So student, yesterday we have seen the emissivity, and what that emissivity is. That emissivity which we have seen, emissivity as a E, which is equal to R upon RB. What is R? This R is nothing but, we have seen the explanation of this R is nothing but the emissive power of ordinary body, and RB is nothing but the emissive power of perfectly black body. Is it right? And then we have seen that is for perfectly black body, your emissive power RB, E is the emissivity, and A is nothing but the coefficient of absorption. So for perfectly black body, your coefficient of absorption is equal to nothing but the coefficient of emission or emissivity. So that law will be applicable for a constant temperature. So if we are going to consider the temperature factor as a constant, then at constant temperature, for coefficient of absorption is equal to emissivity, or at a given temperature, coefficient of absorption is equal to nothing but the coefficient of emission or emissivity. So that proof now we are going to see under this law. So this law is given at a given temperature. At a given temperature means we are keeping the temperature of that particular enclosure as a constant. At that time, coefficient of absorption is equal to nothing but the coefficient of emission. Now that theoretical proof you have to see under the heading as a Kirchoff's law of heat radiation. Right? Now already student, don't get confused in the Kirchoff's law. Already we have seen current electricity, and under that current electricity we have seen Kirchoff's laws for electricity. That is Kirchoff's current law, Kirchoff's voltage law. But that Kirchoff's laws are in case of electricity, and this Kirchoff's law is in case of heat radiation. Right? So don't get confused. This Kirchoff's law we are going to study for heat radiation. Now, what is the thing we are going to consider? We are going to consider a constant temperature enclosure. So this is double walled constant temperature enclosure. So I can label it as a constant temperature enclosure. Inside that, I am going to hold two bodies. One is perfectly black body, and another is I am going to say as an ordinary body. So O for ordinary body, B for perfectly black body. For ordinary body, coefficient of absorption is A. Clear? Then this ordinary body will radiate certain amount of heat energy. At the same time, this perfectly black body will also radiate the energy. So ordinary body will radiate the energy that will be absorbed by perfectly black body. Perfectly black body will radiate the energy that will be absorbed by the ordinary body. Right? And as it is a constant temperature enclosure, so what rate of radiation of ordinary body is equal to rate of absorption of ordinary body. And for perfectly black body, rate of radiation, or I can say that rate of emission of perfectly black body is equal to rate of absorption of perfectly black body. Now for perfectly black body, absorption, coefficient of absorption is 1. For ordinary body, coefficient of absorption is A. Clear? Have you got this idea? So now, what I will write here first, I will write down for ordinary body. So I will say for ordinary body. that is O body. What I say that rate of absorption. Rate of absorption is equal to rate of emission. Right? So what I can say that heat energy in that rate of absorption, heat energy absorbed rate is equal to heat energy emission rate. Means what I say that amount of heat absorbed. In another language, what I will say here, amount of heat absorbed is equal to amount of heat emitted. Is it right? Now amount of heat. So what I say that how much heat energy? Heat energy is nothing but Q. So what I say here, amount of heat absorbed. Amount of heat absorbed is nothing but A into Q. That is nothing but the amount of heat absorbed. How I am going to write this? This is from amount of heat absorbed is equal to total amount of heat incident divided by coefficient of absorption. So what I will say that here total amount of absorbed heat is equal to A amount heat is nothing but Q into A. Because we are knowing, what we are knowing? We are seeing that is coefficient of absorption A is equal to QA upon Q. This definition we have seen. So what I say that amount of heat absorbed QA is equal to A into Q. So A is the coefficient of absorption of ordinary body. So amount of heat absorbed is nothing but AQ. It is equal to, what is that? It is equal to amount of heat emitted. How much amount of heat will get emitted? So now amount of heat emitted is called as emissive power, which is nothing but the R. Is it right? If you are remembering, I will write the formula here. We have seen emissive power can be written as amount of heat emitted per unit area per unit time. That we have seen. That is nothing but your amount of heat emitted. That is emissive power. So that emissive power is nothing but R. So this is nothing but my equation for ordinary body. Got it? Similarly, now I can write down the equation for black body. So I will say for perfectly black body. Perfectly black body. For perfectly black body, same thing I will write down. What I will say? Amount of heat absorbed must be equal to, what is that? Amount of heat emitted. Is it right? Now same amount of heat absorbed. Again I can use same formula. What is that? For perfectly black body, coefficient of absorption is 1. So what I get, 1 is equal to A is equal to QA upon Q. So what will be here? I am getting A value is equal to 1, means I will write down QA is equal to Q. Amount of heat absorbed is Q. So what I say, amount of heat absorbed is Q. It is equal to amount of heat emitted. That is nothing but the emissive power of perfectly black body. So emissive power of perfectly black body is nothing but your RB. This is my equation number 2. Now if I take the ratio of these two equations. So if I take the ratio of these two equations, then I am going to write down, see here, AQ upon Q. AQ upon Q is equal to R upon RB. QQ factor will get cancelled. What I am getting? A is equal to R upon RB. A is equal to R upon RB. This I am getting here. And what is our definition of emissivity? Emissivity definition, E is equal to R upon RB. Right? See here, right hand sides are same. Means their left hand side must be equal. So what I say that this is equation 3. Here is my equation 4. So from equation 3 and 4, I am going to say that A is equal to E. And this is to be called as your Kirchoff's law. That is a theoretical proof for Kirchoff's law of heat radiation. Clear? So this question can be asked for 3 marks along with statement. Fine? See that. What is that? The question will be state and prove Kirchoff's law of heat radiation. So Kirchoff's law of heat radiation. First statement. What is the statement? At a given temperature, coefficient of absorption is equal to coefficient of emission or emissivity. Right? How you can prove that? For that proof, I can consider this example. This is rectangular constant temperature enclosure. Means inside the enclosure temperature is constant. Inside that enclosure I am going to keep 2 bodies. One is ordinary body, another is perfectly black body. For ordinary body, both the surface areas are same. For ordinary body, coefficient of absorption is A. For perfectly black body, coefficient of absorption is 1. Now, whatever amount of heat absorbed by ordinary body is equal to amount of heat emitted by ordinary body. Why? Because temperature is constant. So, emission rate and absorption rate, both the rates are same. So, I can write it here. That is, at constant temperature enclosure, the rate of absorption must be equal to rate of emission. Now, for ordinary body, what I will write down? Amount of heat absorbed must be equal to amount of heat emitted. From definition of coefficient of absorption, amount of heat absorbed is nothing but A into Q, and amount of heat emitted from the definition of emissive power is R. That is the equation number 1. Now, for perfectly black body, same thing happens because perfectly black body is also in the constant temperature enclosure. So for perfectly black body, whatever amount of heat is absorbed must be equal to the amount of heat emitted. So I write down one. Amount of heat absorbed is equal to amount of heat emitted. Now amount of heat absorbed is Q. Why? Because coefficient of absorption for perfectly black body is 1. So in the definition of coefficient of absorption, small a is equal to capital QA upon capital Q. उसमें अगर हमने a is equal to 1 डाला तो QA is equal to Q. So that's why I'm saying amount of heat absorbed is Q. And amount of heat emitted by perfectly black body is the emissive power of perfectly black body. That is RP. So I can take the ratio of equation 1 and 2. अगर 1 and 2 का equation लिया तो left side में क्या होता है? Q factor will get cancelled. And what I will get? A is equal to R upon RB. So that I have written equation number 3. Right? But from the definition of emissive power, emissivity is equal to nothing but R upon RB. So now concentrate equation 3 and 4. The right hand sides are same. Means left hand side must be same. So left hand side क्या लिखा है? A is equal to E. But when? In constant temperature. Therefore, the law is stated that at a given temperature, coefficient of absorption is equal to coefficient of emission. Clear? So, this is called as a theoretical proof of coefficient of theoretical proof of Kirchoff's law of heat radiation. Got it? Fine? Okay. Then, now I am going to start the spectral distribution of perfectly black body. Spectral distribution means what? Whenever a perfectly black body will emit the heat energy, that heat energy will be in the form of electromagnetic waves, and as it is in the form of electromagnetic waves, so that topic will be studied as a spectral distribution. Spectral distribution of perfectly black body. In that, now we are going to consider three important points. What is the first point? The first point I can say that as a hot body radiates electromagnetic radiation. Hot body radiates waves which is nothing but the electromagnetic radiation. This electromagnetic radiations will cover higher frequency range, or I can say that longer frequency range. Is it right? Frequency range बहुत बड़ी है. Now I have to distribute that frequency range, and that distribution of frequency range is, that is, if temperature is low. Now I distribute the thing. If temperature is low temperature means what? It will radiate. It will radiate what amount of energy? The radiated energy, power radiated. I will say power radiated is less. Power radiated is less. Meaning is that when the power radiated is less, means automatically that will lies in the longer frequency, longer wavelength range. Longer wavelength, shorter frequency range or region, I can say. But as temperature will goes on increasing, as temperature will become high, if high temperature will goes on increasing, means that body will radiate more power. So it will radiate more power. The radiation rate will goes on increasing. As radiation range will goes on increasing, then whatever electromagnetic waves are emitted, that electromagnetic waves are goes into the shorter wavelength region and higher frequency range. So for any body, because what Prior's heat theory says that all body emits and absorb heat radiation at all temperature except absolute zero temperature. So same concept is here. अगर कोई भी बॉडी आपने लिया है, उसका टेम्परेचर लो है, if temperature is low, it will radiate less power. Power radiation is less, तो वहाँ पे जो electromagnetic waves आएंगी, that will be of longer wavelength, shorter frequency. If temperature of that body will goes on increasing, so power radiation increases, so that radiated powers are in the form of electromagnetic waves. That electromagnetic waves has a shorter wavelength but higher frequency. And if I am going to say a moderate temperature, in between that, if there is a moderate temperature, so at that moderate temperature, power is also moderate. So that electromagnetic waves will radiate the mixed type of radiation. So it consists of higher range of frequency, lower range of frequency. So there is a mixture of wavelength. So that mixture of wavelength will take place at the moderate temperature. And therefore, the scientist has tried to plot a graph of radiated power with respect to corresponding wavelength. So as your radiation power will goes on increasing, the wavelength will become more shorter and shorter. Is it right? So that graph is plotted, and that graphical presentation between radiated power versus wavelength at a given temperature. And that graph is plotted by a scientist as a Lumber. So Lumber has plotted, Lumber has plotted a graphical presentation of power radiated versus wavelength at a given temperature. So now we are going to plot a graphical presentation. So here I will show you a graphical presentation of energy distribution. तो ये जो स्टेटमेंट है कि आपको एमसीक्यू के लिए याद रखना है. So in that graphical presentation, I will plot a graph of, here I will say that radiated power, here is nothing but the radiant power versus wavelength. ये ग्राफ प्लॉट करना है. Wavelength I will say as a 5,000, then I can call it as a 500 nanometer, 500, 1,000, 1,500, 2,000, 2,500 in terms of nanometer. Nanometer का मतलब है 10⁻⁹ meter. Is it right? Now in that graphical presentation, it is to be seen that is अगर आपका temperature है, if your temperature is nothing but 3000 degree Kelvin, so for 3000 degree Kelvin, somewhere here you are getting a maximum power, and after that this power will goes on decreasing. Your power has to be decreased further. And this presentation of graphical presentation I am getting for temperature as a 3000 degree Kelvin. So 3000 degree Kelvin का यहाँ पे देखो ये peak कहाँ है? This peak is in between 500 to 1000 nanometer. यहाँ पे इसका peak आ रहा है. Clear? Then if I rise the temperature by somewhere I can say as a 4000 degree Kelvin. So इसका पिक और यहाँ पे थोड़ा सा आगे चला जाता है यहाँ पे somewhere. If I plot the next graph of 4000, तो उसका पिक थोड़ा सा यहाँ पे कहाँ तो भी बीच में आ जाता है. So that peak will come somewhere in between 5000 से कुछ आगे यहाँ कहाँ तो भी चला जाता है. This is for 4000 degree Kelvin. अगर आपने बुक में प्रॉपरली देखा तो इसका पिक यहाँ चल जाता है. It is in between 500 to 1000. Furthermore, I am going to increase further temperature, which is nothing but as a 5000. उसको आगे मैंने और 5000 पिक कर दिया. So for 5000, I am getting like this. This is for 5000 degree Kelvin. आगे जाके और मैंने किया. This type of graph I will getting for 10,000 degree Kelvin. तो आपको देखो यहाँ पे if you are seeing for 3000 डिग्री का पिक कहाँ था? 1000 के आगे, फिर 4000 का थोड़ा सा 1000 के पास आ गया, इसके बाद 5000 का पिक 500 के पास आ गया, और इसका जो पिक है दिस पिक और यहाँ पे शिफ्ट हो जाएगा. तो ये शिफ्टिंग देखो कहाँ पे आ गया, अप्रोक्सीमेटली 500 पे आ गया. So this is nothing but the graphical presentation of radiated power versus wavelength. Right? Now from this graph, which conclusion we are going to draw? That conclusions are important as a theoretical question as well as for the MCQ. What is our first conclusion? At a given temperature, energy is not distributed uniformly. यहाँ पे देखो ये एनर्जी कैसे है, इनिशियली एनर्जी 0, फिर इंक्रीज होती जा रही है, फिर स्लोली एक्सपोनेंशियली डिक्रीज होती जा रही है. मीन्स व्हाट आई कैन से दैट एट ए गिवन टेम्परेचर योर एनर्जी डिस्ट्रीब्यूशन इज नॉट यूनिफॉर्म. वो एनर्जी डिस्ट्रीब्यूशन आपका यूनिफॉर्म नहीं है. दैट इज द फर्स्ट कंक्लूजन. What is our second conclusion? Now I can go for the second conclusion. At a given temperature, initially your radiated power will goes on increasing. It reaches to some peak value, and then slowly, exponentially, it will goes on decreasing. So that is my second conclusion. So initially, I can say that initially power radiated increases, then go to peak value, and from that it will decreases exponentially. That is my second conclusion. Then I can draw the third conclusion from that. Third conclusion में अगर आपने देखा, so in that third conclusion I can say that whatever the area enclosed under this curve, this area enclosed under this curve will represent the total energy emitted per unit area per unit time. So the area under curve gives us total energy Q per unit time per unit area. Then fourth one, the fourth conclusion I can say that the peak of the curve, ये देखो ये कर्व की जो peak है, peak कहाँ शिफ्ट होते जा रहे हैं, लेफ्ट में. तो peak of the curves are shifted towards the left. Towards the left shift होते जा रहे हैं. Means what I can say that as your temperature increases, peak radiant power will increase, but the wavelength will get shifted towards the lower side. Is it right? Means as temperature increases, the wavelength will goes on decreasing. Fine? Then the fifth conclusion I can say that at higher temperature, your radiant power corresponds to all the wavelength increases. Higher temperature पे जहाँ पे आप यहाँ पे देखो higher temperatures पे जाओ. So at that higher temperature, see this. यहाँ से 0 से आपका wavelength, ये देखो wavelength range कहाँ से लास्ट कर्व वाले में कहाँ से कहाँ तक wavelength range कवर किया, देखो इतना. So much wavelength range is covered. That is nothing but your last conclusion. That is at higher temperature, the radiation spectrum covers all wavelength. ये देखो यहाँ से 0 से यहाँ तक उसने wavelength कवर किया. Is it right? So these are the important conclusions which you will get in from the graph of radiant power versus wavelength. Is it right? And from this graph, the scientist Wien has given his law. What he says that the scientist Wien has given the relation between here wavelength and temperature. So what he says that is when we are thinking about the radiant energy, at that time I can say that for perfectly black body, the wavelength is maximum. Your wavelength will be maximum. कहाँ पे maximum wavelength है, यहाँ पे देखो. The wavelength is maximum when the temperature is minimum. Is it right? So that law is to be called as your Wien's displacement law. So I'll write down here as a Wien's displacement law. Wien's displacement law. What he says that Wien's displacement law, in that he says that is your wavelength observed for which emissive perfectly black body is maximum. Emissive power is maximum for corresponding wavelength, this wavelength. So for that wavelength is minimum. Is it right? And the corresponding temperature is maximum. Is it right? Means what I can say that your wavelength is minimum at which is inversely proportional to the temperature. So you will get the minimum wavelength at temperature maximum, or I can say that I will get a maximum wavelength. Maximum wavelength कहाँ पे मिला है आपको देखो, the wavelength maximum here I am getting 1000 के आगे है. So wavelength is maximum, but at that time temperature is minimum. So wavelength maximum is inversely proportional to the temperature, and this is to be called as your Wien's displacement law. And according to that Wien's displacement law, I can say that lambda max into T is equal to B. ये B क्या है? B is a constant, and this B constant has a value. The constant B has a value which is equal to 2.897 into 10 raised to minus 3. 10 raised to minus 3 meter Kelvin. That is nothing but the value of B. Is it right? And this law is called as a Wien's displacement law, which gives the relation between maximum wavelength distributed over the temperature. Got it? Any doubt? Clear? And this Wien's displacement law, where we are going to use this Wien's displacement law? We are going to use this Wien's displacement law where you want to find out the higher temperature. That is temperature of sun, temperature of planet, temperature of star. जहाँ पे आपको highest temperature है, where we are going to use this Wien's displacement law. Right? So by this law we can able to determine the temperature of your universal sources, sun, star, planet. That temperature you can determine with the help of this Wien's displacement law. Clear? So here I will finish. I will stop my topic, and next time we are going to see the last topic from this chapter, which is nothing but your Stevens-Boltzmann law of radiation. Got it? तो इसके ऊपर क्या क्वेश्चंस हो सकते हैं? ये ग्राफिकल प्रेजेंटेशन सिर्फ ग्राफ ड्रॉ करने के लिए हो सकता है. So the question will be draw the graphical presentation of spectral distribution of perfectly black body. एक दूसरा 3 मार्क के लिए draw graphical presentation of spectral distribution of perfectly black body and write conclusions. तो जो मैंने 5 conclusions दिए थे वो. And what is the last one? What is or state Wien's displacement law and represent it mathematically, or write the formula for maximum wavelength. Clear? तो ये 3 क्वेश्चन इस पर्टिकुलर टॉपिक पे आपको हो सकते हैं. और ऑलरेडी आई हैव गिवन द Kirchoff's law of radiation.